Welcome, everyone. I want to welcome everyone to the 12th Hans Liebe Lecture. And I want to point out that the first time you run an honorary lecture, you don't know if you're going to have the 12th lecture. So I think right now we can take some stock and be happy that over the past 12 years, we've been able to identify 11 astute members of our society, of our radio science community, around the globe who have been identified as Hans Liebe Fellows. And I have them listed here. And in fact, our first fellow, Dave Turner, is with us today. Great to see Dave here. So we really have something great going over here, and it hasn't at all ended this year because we have our 12th Hans Liebe Fellow, who we'll introduce in a moment. I want to point out that Hans Liebe Lectureship was established with the generous support of the Liebe family, and it is a lectureship in microwave and optical spectroscopy as applied to radio science, Earth remote sensing, radio astronomy, and telecommunications. And when we think about microwave and optical spectroscopy, that definitely involves quantum mechanics, as we will find out today from our speaker. This lectureship supports travel and an honorarium for a distinguished member of the radio science community to deliver a lecture on the professional topic of their interest at each of the annual URSI meetings. And it's an honor of Hans. Hans was a friend of the radio community, a great contributor to the radio community, in particular through his propagation model, which we use in various forms and sometimes almost in its exact original state today for a number of propagation modeling problems. So without further ado, I'd like to introduce our 12th Hans Liebe Fellow, which is Dr. Christopher Holloway from the US NIST. Dr. Holloway is the group leader for the Electromagnetics Field Group and project leader for the Rydberg Atom Sensor Project, both at NIST. He has been at NIST for over 25 years and is both a NIST Fellow and an IEEE Fellow. He is also in the graduate faculty at the University of Colorado at Boulder. I will point out that Chris occasionally teaches our undergraduate electromagnetic courses there. Thank you, Chris. And I only found out afterwards that Chris also worked for Hans some time ago when he was at ITS. So there's a very strong connection here. He is an expert in electromagnetic theory and metrology, quantum optics, Rydberg atom systems, and atom-based sensors. And he has a publication index that I think you need a logarithmic scale to begin to really describe. Of 64. H of 64 is quite good. He has 10 patents in various fields. He has been involved with URSI for over 30 years, in various capacities. So without further ado, I will introduce Dr. Chris Holloway, who will talk to us about Rydberg atom sensors, transforming measurements, and detection of radio frequency fields and time-varying signals. Chris.
Thank you very much. There we go. Well, first I want to say thank you so much. It's an honor to get this fellowship for various reasons. One reason is that I actually worked with Hans. Before I was at NIST, I was at ITS, and I worked in his group. And besides being a great scientist, he was a great mentor and just a great human being. He was always willing to answer any questions out there. So it was really a privilege. One of my highlights at ITS was actually working with him. Before I get started, I also wanted to say URSI is a great society, and for the students or early career, I'd say stick with it. My first technical presentation was at the URSI student paper competition maybe 1 or 2 years ago, something like that. But with that, what I want to talk about today is Rydberg atom sensors. And the idea here is we're going to use atoms to make a direct measurement of an electric field. And we're going to see that besides being able to make direct measurements of electric field, it opens up a whole array of really interesting applications. And that's what I'd like to talk about. You know, maybe before I get started, I should say, why was someone with a theoretical electromagnetic background go into atomic physics? And I would say I credit or blame CU for that. I got my PhD here, and I think I saw Ed, my advisor, there he is in the audience. Don't take offense what I'm going to say. But when I was here taking my graduate level electromagnetics courses, We talked about fields a lot, but I never got a warm fuzzy that we really knew how to measure fields. We never did a direct measurement of a field. We basically have a probe or an antenna. We wanted to measure a field. We'd have to calibrate this device somehow, stick it in a field, and we'd measure it. Or for me to calibrate this, somehow I would generate a known field, so I could put this device in there to calibrate it. Well, how do I know what the known field is? I maybe go out and buy the same probe, put it in the field to measure it in the first place. So we had this chicken and egg problem. And I graduated, went to ITS, and then to NIST, but this whole problem of not being able to measure an absolute field bothered me through the years. And probably about 15 years ago, I started realizing if somehow we could do a measurement of a field, and if we could tie it to an atom, because an atom's fundamental, the physics are the same for an atom as here on Earth, up in space. If we go to DC, it might be a little different. Physics changes there a little bit, but for most other places, physics are basically the same. And the atom behaves in any environment we put it in. It responds very well to that environment. So if we can figure out how to read out the response of that atom, we have a very good electric field sensor. So I proposed this idea, and no one was interested. I couldn't get a dime, so I had to beg, borrow, and steal equipment about 15 years ago to start this project. We did some proof of concept, showed that it worked, and started getting some seedlings from DARPA and some other government agencies. Now, in the past, I would say 5 years, there's probably, I could give you 15 to 20 US companies that have started programs in this field, and we'll see why they're doing that in just a moment. My group in particular, I started this project 15 years ago with just me. Now we have 14 full-time people in the lab working in this field, various applications, parameters we're looking at. And we started this really for the pure purpose of coming up with a direct measurement that's, we would say, traceable to the SI for measuring a field. Well, fortunately or unfortunately, 99.9999% of the world could care less that we could make a traceable direct measurement of a field. So why in the past 5 years have people gotten so interested in this? And I'm going to start by showing a video to say why. And I have this up here. If you're a manager or a bean counter, you might want to close your eyes for a few minutes, because when I show you this video, the reason is, as you see, this is my lab across the street. And here we are, we're in the lab playing a video game, right? Maybe. There we go. We're playing this video game in the lab. Nice, crisp color, no latency in the game. We're playing it. And so if you were a manager or bean counter, you might be concerned that we're in a $4 million lab playing a video game all day. Well, it turns out it's not how or why we're playing the video game in the lab, it's actually how we're playing it. And how we're playing it basically is, we took the video game, we AM modulated a carrier. This carrier, then we shined it onto this glass vapor cell here. It's basically full of rubidium atoms. I'm not sure why that slide did that. Let me go back. And the idea is that I basically shine a laser through here. This laser, I put two lasers through here. I excite these atoms to a Rydberg state. When these atoms are at this Rydberg state, when I apply an RF field, I basically modulate the atomic state of that atom. And by just shining a laser through here, I can take the laser, put it on a photodetector, output of the photodetector, put it onto a monitor. Basically, what's happened here, the atoms act like the antenna, so you eliminate the antenna. So half of this conference we don't need anymore. So the atoms act like the antenna, and more importantly, or equally as important, they automatically do the downconverting and demodulation for you. So therefore, you eliminate a lot of front-end electronics in a receiver. That's what got a lot of people interested in this. You know, we're going to see, we're not going to be replacing this, but there's some applications where this could be very useful. And that's what I want to talk about. So let me get started by saying that whenever you're doing sort of cool research, sometimes you have arguments in the lab of who gets to be the first author. This paper was easy. Everyone in the lab played the video game, and the one with the high score got to be the first author. So it was a very easy way to determine that. If you're interested, we actually have a demo in the lobby that we set up this morning. If you have time, walk over there. We're going to keep it up to about 2 o'clock. And you can actually see a streaming video right over the atoms. Once again, no antenna, no demodulation electronics, and so forth. So it's just an interesting concept here. So I want to try to explain what's going on. But before I do, I thought I'd just give a couple slides of who NIST is and what we do. So I'm at NIST. We have 2 facilities. There's about 3,000 people in Gaithersburg, Maryland. There's about 600 people here in Boulder. I've got an arrow showing my lab here. And our mission in life is really to benefit U.S. industry. And what we do, basically, we keep track of all the weights and measures for the country and also tied to weights and measures around the world. But we also do sort of fundamental research looking at what technologies might be coming online 15, 20, 30 years down the road. The one question you might ask is, why do we need standards? A good example is that just east of here in eastern Colorado, there's a lot of beet farmers who grow beets. And these beet farmers may grow their beets, put them in a bushel, they weigh it. Maybe they want to ship it overseas, they take it to a port, it's weighed there. It gets to the country of choice, they weigh it. You hope that all 3 of those scales give you the same volume. And so, a good example is when NIST first got started, its precursor, which is the National Bureau of Standards, and I think it was in 1902. If you went around the country, you could collect 40 different volumes that people were saying was a U.S. gallon. So there was no standards even in the U.S. back in the 1800s, end of 1800s. How we ensure that we're all making the same measurement, we tie our system or our measurements to something called the SI, the International System of Units, and it's governed by this body out of France, the Bureau of International Weights and Measures. An interesting anecdote is, does anyone know why we don't have the metric system in the U.S.? I blame it on pirates. It turns out, this is a true story, that right after the Revolutionary War, Thomas Jefferson wanted to ensure that we had some system of weights in the U.S. And the story is that he liked the French system. I think he was just trying to get back at the Brits. So he sent a bunch of money to France to buy some artifacts, a meter stick, a kilogram ball, some type of leader, put them on a ship, sold them to the U.S. Just off the east coast of the U.S., pirates took over the ship. They also sent a scientist over to show everyone how to use these new weights and measures. They put the scientist into prison and tried to blackmail the U.S. and France to get him out. And he died like a week in prison. So they decided to just get rid of the artifacts. Some of them were thrown in the ocean. They distributed whoever knew where they went. The U.S. didn't have any more money to send to France to get new artifacts, so we're stuck with the Queen's system here. But anyhow, so what is an artifact? An artifact is just a way of measuring something. The meter stick, mass. Here's the U.S. bushel in 1857 rather. You can actually see this if you go to the museum in Gaithersburg, Maryland. So this makes sense to have something we can intercompare. The problem is, it sounds like a good idea, but these artifacts change. So we need something that doesn't change if we're going to do traceable measurements. And what we do now is use basically an SI system of units. And before 2018, the last artifact was the kilogram ball. That's now no more. All the systems of units now are tied to fundamental constants in nature. The one constant that's interesting to us is Planck's constant. And we're going to see with Planck's constant, we can make an SI traceable measurement of field and RF power, which is what we're interested in here. Another interesting I always like to show this is why are measurements needed? I was at a meeting back in 2 BC. This is 2 years before COVID. I was in Las Vegas, and I saw the sign. And I would argue that's like saying NIST has the largest second or NIST has the longest meter. In reality, pint's pint, unless you're in Europe, and a second's a second. So, how do we do, what we're interested in is electric field, so how do we really make a traceable measurement of an electric field? And, as I said, the motivation here was this chicken and egg problem. To calibrate a probe, I have to have a known field. To have a known field, I have to have a calibrated probe. And there's ways that we generate what we think is a known field. We still believe Maxwell's equations are correct. We have a horn antenna. We've calibrated this horn. We have some cable. We've calibrated the loss. We know the input power. Maxwell's equation tells us some distance, at some point here, we know what the field is. We stick a probe in there and calibrate it. But on a really, really good day, we can do this to about 5%. Typically, in industry, when they do these measurements, we're talking about 10% error in generating a known field. So we'd like to do better than that. And can we? And yes, we can. We can do that by using an atom. And the idea is that atom responds very well to the environment you put it in. And the question is, how do we read out how this atom is behaving when it's in an electric field? And we're going to use something called Rydberg atoms. And maybe a little example why we want to use a Rydberg atom. If you remember back in your atomic physics courses, that an atom is basically got some nucleus, got some electron moving around. If you take this electron and move it up to a very high energy state, move the electron really far from the orbit, you have a big dipole moment. And therefore, this dipole moment is very sensitive electric field. It makes a very good electric field sensor. And in atomic units, we're talking about these Rydberg states have dipole moments on the order of 10,000. It's very, very, very large. So that means they're very sensitive to electric field. They make very good electric field sensors. And we just have to figure out how to read out the response of these atoms. And we do this with something called electromagnetic induced transparency. And what that does is it allows us to read out the atomic state that the atom's in. And when we apply electric field, it basically modulates that atomic state, and we can measure that with lasers. And there's different ways we do the readout, and I'll talk about a few of these. But the basic idea that we're trying to do is take your conventional antenna or probe that's got worries about conducting electrons bound to some metal surface, and we're replacing it with just a glass cell of atoms and looking at basically the atomic state of these atoms, and we hit them with a field. A little bit of perspective here. Like I said, prior to about 2010, people knew that these Rydberg atoms interact with electric fields and it changes the state and so forth. In 2010, we wrote a paper that talked about that if we could make a measurement based on these Rydberg atoms, we'd have a SI traceable probe. And then DARPA started funding a couple of groups. There was my group at NIST that they funded and a group at Oklahoma. And we started working on this, started making a lot of progress, especially after about 2014. We started making huge gains. And now, because of all this progress and success, there's numerous groups now around the world with these, trying to make these sensors. There's government agencies, there's universities, private companies, and so forth. And I just have a few listed here of who's working on this. And just as this slide here is probably about 5 years old. I can give you about 15 different companies here in the US that are doing this. So there's a lot of interest in this. Let me try to explain what we're doing here. And since this lecture is on spectroscopy, that's really what I'm doing. I'm doing atomic spectroscopy here. The idea is to have this glass cell. I basically shine a laser through the glass cell. I look at the power in the photodetector. I put a second laser here that drives this atom to a Rydberg state. And I can look at the change of the power of this probe laser, and that tells me something about the atomic state that the lasers or that the atoms are in. And we can represent that as basically a 4-level atomic system. And from an atomic physics viewpoint, it's a very simple experiment. It's all done at room temperature. This is a plot of power on the photodetector versus wavelength of this coupling laser here, or this probe laser here. And so if I scan this laser across this first atomic transition, when I'm on resonance with the atom, I have very little power on the photodetector. Basically, I have absorption. The trick is if you turn on this second laser, you get this interference, sort of a quantum interference between this 3-level atomic system here. And what happens there is you have a medium that was normally normally absorbing, it becomes transparent. And this is called electromagnetic induced transparency. Basically, we've taken a medium that was normally absorbing, put it on a second laser. I basically make that medium transparent over a very narrow window. And people have known about this for a number of years. Our trick is we choose this color light here such that we drive this atom up to this Rydberg state. When it gets up to this Rydberg state, now an RF photon can couple into the next atomic level. And what happens there is that when we do that, we basically alter the atomic state. And basically, this EIT line splits into two. And with a little bit of atomic physics, we can determine what the separation of those lines are. And basically, what we can see is that the splitting is directly related to the applied amplitude of the applied field, and this is on the order of megahertz. We turn that around, it says if I basically can measure this separation between these two peaks, I know Planck's constant and I know the dipole moment of the atom, I get a direct measurement of the field. And this is what we would refer to as a direct SI traceable measurement of field, because it's basically we've taken an amplitude measurement, turned it into a frequency measurement, and somewhere, yeah, the traceability comes because we have Planck's constant. So Planck's constant's a known. The frequency is something we can measure quite accurately. And the only unknown is the dipole moment of the atom, which we think we can calculate to about 0.1%. So our quantum uncertainty here in doing this measurement is 0.1%. So we already improved an order of magnitude over what we do now. Maybe 2 orders of magnitude what we're doing now in the lab. From an experimental viewpoint, it's a very simple experiment. We have a vapor cell. We have a laser that we probe the atoms with. We have a photodetector. We have a coupling laser. And then we basically have a horn antenna that we apply some field to here. If we look at the power, if we look at the output of this photodetector, we get something like this. And what this is showing is that if I turn on power onto this horn antenna and I monitor the atoms here with this vapor cell, this is how this splitting occurs as we slowly increase the power. So our experiment is just measuring the separation between these two peaks, no Planck's constant, dipole moment, I can tell you what the fields hit the atoms were. And our proof of concept that we did about 2012, I think, was this curve right here, which showed where I took basically a horn antenna, vapor cell. From Maxwell's equations, I could determine what the fields are. Maxwell's equations is a solid and dashed curve. This is the power feeding the horn antenna. This is the field that we measure or determine with Maxwell's equations. The circles are based on this atom-based approach. And you see very good correlation. One of the things that got people initially interested in is this curve here. You see I've got data on here from 9 gigahertz up to 182 gigahertz. With one of these vapor cells, we can basically measure fields from DC to daylight. And so if you think about the number of antennas you would need to basically measure from, say, 1 megahertz up to a terahertz, you would have to have numerous types of antennas and sizes. This one compact vapor cell does that. So the idea that it's a very broadband sensor, and the fact that, we say 10, I used to say 10 megahertz to a terahertz. Now we're down to 20 kilohertz in the lab. Just recently we've measured 20 kilohertz in the lab. So it's a very broadband sensor. And we're going to see, as you can see, it's also at these really low frequencies, it's a true electrically small sensor. And there's some calibration aspects of this that, now we actually think we have ways of doing calibrations above 110 gigahertz, which you can't do right now presently. This is some data that I data mined after our first set of papers. A lot of this is our data, but it's other groups around the world now that are starting to do these experiments. This gives you an idea of the frequency range versus field levels that people are measuring with these sensors. Obviously, there's a sweet spot here in the tens of gigahertz range. This plot here shows how we're improving the sensitivity as time goes on. And now, one of these dots down here is our results, but there's other universities and groups that are trying to improve the sensitivity as well. It just gives you an idea of what you can do with this. Well, if you can measure an amplitude of the field, you can actually do AM and FM modulation, because the atoms actually do a lot of down converting for you. The idea is that if you have a CW signal, you turn on a field, you get some splitting. If you modulate that field as an AM sense, these two peaks wobble back and forth. So if you can park your laser on one of these lines, the output of that photodetector is just the baseband signal. And so we demonstrated this, various other groups have demonstrated this, and I could give you all sorts of curves here to show how well the demodulation is, but I figured we'll use another sensor we all have, and that's our ear. So late one night when the managers were gone again, I brought my acoustic guitar into the lab that had electronic pickup. I took this electronic pickup, I AM modulated a carrier, shined it onto one of these vapor cells, put a laser through it, took the output of the photodetector, and put it on a set of speakers. And this is what one can hear. So I'll let that breathe. You can enjoy my solo, A minor, by the way, if you're interested. And what you need to hear here is you hear a lot of highs, a lot of lows, a lot of dynamic range here. If you listen carefully, if I'm quiet, you hear some humming. That's basically the laser noise. I like to call it as an atomic acoustic effects pedal. But the idea here, the subtleness that I want you to realize is that there's no antenna picking up this AM modulated carrier, right? It's just this vapor cell. The atoms are your antenna, and the atoms automatically down convert, and the output of this photodetector is the baseband signal. So just an idea of how these things work and what some of the advantages are. And another example is we basically took a camera, AM modulated carrier, put it on the vapor cell. We're at a point now where we've got the bandwidths up that we can actually start doing color. So this is basically the AM modulated carrier being picked up on a photodetector. We take the photodetector and put it right into a CRT monitor, and basically This is us in the lab. There's our camera, waving at the camera and streaming it right over the atoms. Once again, no antenna, no demodulation electronics and so forth. And we showed the video. The thing is I wanted to get at that now we're starting to understand these atomic systems well enough that we can control the bandwidth at which they work at. We can send video over these atoms where we can have very blurry figures, very blurry black and white. We can go to sharp black and white all the way to sharp color. To get color here with this modulation scheme, we need about 6 megahertz of bandwidth. So it sort of shows what we're picking up in the lab. We've got about 6 megahertz of bandwidth. Currently, our best bandwidths are about 10 megahertz. And there's some reasons if we may or may not be able to go above that, but we can talk about that if we needed to. More of a historical perspective, up until about 2018, most people were doing just amplitude field measurements because we could not figure out how to do phase yet. There's some groups looking at polarization, and from that we could do AM and FM modulated carriers we could pick up very easily. The missing link was phase, and about 2019 we figured out how to measure phase. We put out a paper. Now it can fully characterize a signal. We do amplitude, phase, and polarization in one compact vapor cell. And to sort of do a little bit of, we do like to have fun in the lab, so we tried to do a few things here. One thing, let's talk about how we're measuring phase, and we do that by making something called a Rydberg atom mixer. The idea here is that we take this vapor cell, I basically have a LO, I shine onto the atoms, I have a signal I'm trying to detect. These two signals create a beat note, and the atoms pick up that beat note automatically. And basically, this is the output of a photodetector of some CW with an LO. And if I change the relative phase of this carrier here, I can actually change the phase of the beat note. So by doing that, we can actually measure phase very easily. And for a cute trick, the first thing you want to do is, can we measure propagation of free space? So we took a antenna right here, put it on a translation stage, measured the phase as we moved the antenna away from our measurement point. And if we could measure phase versus distance, we could get propagation constant. And this is our data. This is right off the photodetector, a varying phase as we move across. If we move the antenna, we can plot distance versus phase, take the ratio of that, take the slope of that, and we can measure the propagation constant. Our mixer tells us is 409.3. Theory tells us 409.7. So it shows we can actually measure phase quite nicely. But the real trick is, can we really do a phase modulated carrier, much as like what your cell phone would do? So what we did is we took 247 random bit streams, shined them over the atoms, and we looked at various different modulation schemes. And what I'm showing here is the IQ diagram. It's basically showing how well we can resolve these different phase states. PPSK is basically 0, 180, 4 phase states here, and we show we can go up to 64 QAM. If you think about it, it's pretty impressive. We can measure 64 different phase and amplitude states by shining basically a modulated signal right over these atoms. And once again, the subtleness here I want you to remember is that there's no antenna involved in this system, and the atoms are automatically doing the down converting for us. So we're saving some front-end electronics here. This is just a cute little example where, if it's going to work, there. That we can show, we can just put a cell phone right up to these sensors and pick up. And what you're seeing here is this is the output of the photodetector. So I can pick up the signal right off the photodetector. It turns out what this LO also allows us to do, because we're generating this beat note, it allows us to get very sensitive field measurements. Right now, we can measure fields. This is a technique we developed like in 2019, I think. This is the common approach now people are using to try to get weak field detection. Right now, we're down, we can do, about 2 to 3 to 5 microvolts per meter, very readily in the lab. And so there's a lot of work right now trying to see how far below this detectable fields we can get right now. So with that, like I said, we can measure amplitude, phase, and polarization, and that's great for an SI traceable measurement. It's great if we want to do modulated signals and so forth. But it turns out there's a whole range of other applications that people are looking at, including us. One of that is now we can do angle of arrival. By actually taking a vapor cell, put a couple of laser beams through there, we can measure the relative phase between these 2 points, and now we basically have a phased array. So now with this, we can easily measure angle of arrival by noting the phase at various locations inside a vapor cell. We're looking at doing now a voltage standard. We've actually have vapor cells we put parallel plates in. If I actually put basically a voltage across these parallel plates, it generates a field. If I can measure the field inside between these two parallel plates inside the vapor cell, I can measure basically the electric field. And what happens here, we use a different technique called Stark shifting as opposed to this EIT approach, this ultrasound splitting approach. But the idea here is that we can actually now start looking at possibility of making very compact voltage standards. We're looking at power. Can we measure power? And we know from our basic field theory that the fundamental mode in a waveguide varies as sort of sine wave. Got some peak value. If I could measure this peak value, if I can measure this peak field with a little bit of with Maxwell's equations here, I can determine that if I can measure this field, if I know the geometry and how much the materials I'm filling the waveguide, I could get power. And if I could use an atom-based approach to measure this, I could then get a SI traceable measurement for power, directly right to the atom. And we've done that. Took a rectangular waveguide, filled it full of atoms, put some lasers through there, and now I can actually measure power. This is a correlation between power measured with the atoms versus what you would get from a power head reading. And the reason why this is important is that we're trying to come up with a new paradigm shift in measuring power. Right now, if you think either optical or RF power, typically when you measure it, you have to disconnect your cables, put your power head on, do a measurement, and then put it back in and do your experiment. We're actually trying to incorporate these Rydberg sensors right into an RF source, so you can have a calibrated power as you're doing your experiment or your measurements. You would have actually an in situ SI traceable measurement of power. Now, if everyone probably in your pocket has a very nice camera, right? Wouldn't it be great to have an RF camera? Maybe it wouldn't be great if you had all the fields floating around here. But we take a snapshot of the magnitude and phase as a function of distance or in a plane. And we're actually building, this is our first prototype over here. It is basically, I think this is 20 by 20 by 2 millimeter thick cell. Inside here, we're able to interrogate 100 different points inside the cell. So this is basically our first attempt to try to make a two-dimensional snapshot of magnitude and phase of the field. This is designed at 26 gigahertz. Obviously, we could do it at other frequencies, but it's the idea of trying to make, if you want to think of it as an RF beam profiler. Related to that is now we've got a brand new paper that we just submitted to Nature, where we're actually now able to do really nice, I'll say, very nice resolution images, two-dimensional images of RF fields. And in this example here, basically, we took a microstrip line, cut it into the shape of NIST, drove current through it. We put our atoms on top of this strip here, and we're able to monitor the fields across this printed circuit board line. And you see our resolution is about 50 microns. Now, there's a whole range of topics that us and other groups are working on. One, the main thing is sensitivity and low frequency. Those are the two driving things right now. Bandwidth's out there, but at low frequency, bandwidth's not as important as at higher frequency stuff. So right now, there's a driving factor is sensitivity. How do you get these things more sensitive? We're looking at sort of I call it atomic physics approach of doing optical repumping, 3-photon fluorescences, 6-wave mixing schemes. And then we're doing electromagnetic approaches where we're actually taking these vapor cells and embedding them into waveguides and small split ring type resonators to improve sensitivity. And then the idea we can now start addressing the atom by putting multiple RF fields on the atoms. We can perturb their states in such a way that now we can start measuring low frequency fields. And this is just an example of some technique. I'm not going to get too much into details. The bottom line is now we're able to demonstrate that we can measure with one of these small 4 millimeter size vapor cells a 20 kilohertz signal. And if you just think about the size of a resonant antenna you might need at this frequency, I would say we now have a truly electrically small sensor. So we're more NIST approach of things that we're looking at is that as we can do black body detection now. And from that, we're looking at making a new temperature standard. The idea that if you have a group of atoms that you excited to a Rydberg state, if you let them sit there in some black body field, all these atoms are going to get redistributed in various other states due to blackbody radiation, and then they basically are going to eventually decay to ground state. If you can measure the relative populations of the different states that the black bodies put the atoms in, we can measure temperature. And this is a paper that I guess is coming out next week. Correct, Noah? I believe it'll be out next week. But basically, we've demonstrated this actually quite successfully. We basically generated some Rydberg atoms. We let it set in a black body field. This is basically room temperature field. These atoms basically repopulate in these various other states. We can actually measure the relative population by doing something called selective field ionization. We can measure the particular atomic states, and from that, we can get a plot that allows us to determine temperature. Right now, we're about 1 to 2 K temperature resolution. We hope with some systematic improvements, we're going to get this much lower. But the idea that now we're starting to understand these systems well enough that we can start doing a whole range of other topics. For this to be viable, obviously, we've got to move it off the optical bench. You know, most of our experiments right now, us and other people are doing everything on an optical bench. Obviously, that's not very attractable. What we're doing now is making these fiber-coupled cells that allow us to move the probe off the bench. This is basically a 10 by 10 cubic cell that has fibers coupled to it that we can run our lasers through, and we can move this off the bench and do various measurements. And we've done various things of putting in anechoic chambers, measuring fields on printed circuit boards, antenna measurements, and so forth. But we eventually like to make everything smaller, and this is our first attempt of a portable system here. That basically, this is a system that has all the lasers, electronics, and everything you need. You know, eventually the goal here is get everything down to a deck of cards. And we're almost there. We're halfway there. One of the lasers is already a chip scale laser because that's the laser that's in the chip scale atomic clocks. If you've ever seen them, these are atomic clocks about the size of a stack of quarters. All the photonics and everything, the electronics, the vapor cells can all make compact. The one hurdling factor is one of the lasers. We're still trying to make that smaller, and other people are trying to make that smaller. But the idea that eventually we hope to get this thing down small, and this is our first attempt at doing that. And a selfish plug, if you want to come to the lobby again, we've got a demo running there. We'll probably keep it there at about 2 o'clock if you want to see this in real action. We're also looking at trying to do basically making very compact vapor cells. You know, this right here is, you know, where it's small, we'd like to make these things smaller. And when I say small, we'd like to get vapor cells on the order of maybe 4 by 4 by 4 millimeter, maybe 2 by 2 by 2 millimeter type cells. And this is sort of the first attempt at trying to get there. In fact, DARPA has a program right now that they just kicked off. They got various groups trying to figure out how to make these cells very small. It turns out there's some subtleties of how these Rydberg atoms interact with walls and so forth that makes this a difficult problem, but it's something that us and some other groups are looking into. So for a summary, you know, like I said, over the past few years, great progress has been made. I have to admit, a lot of that's been made at NIST, but there's now many other groups now starting to contribute to this field quite a bit. And because of this progress, there's numerous groups around the world. You know, I said there's other national metrology labs besides NIST, private companies, universities, other government labs that have now started programs in this. In fact, it seems like weekly I have a company or a university call and asked how to get started in a lab and getting these going. And feel free to call me. You know, our purpose in life at NIST is disseminate information, so we'll tell you exactly what we're doing as long as we publish it first. We'll be happy to tell you what we're doing. But I like to group these technologies into 3 sort of general areas. You know, these Rydberg sensors, I see from a metrology viewpoint, we're talking about traceable field measurements, traceable power measurements, and black body detection, and then voltage measurements. There's also the idea that really what most people are interested is the communication aspects. You know, how can these receivers be used to give you some benefit over something that you're not already doing? And that's what us and some other groups are looking at. And the idea you can do AM, FM, phase modulated, stream video, all sorts of types of communications. Then there's these other applications that us and other groups are looking at. And we talked about black body, subwave lift imaging. We just showed a couple of imaging schemes that we're working on. And you know, the eventual goal here is people are actually trying to see if we could actually make spectrum analyzers and waveform analyzers for these Rydberg sensors at the lower frequency end. So there's a whole range of application spaces people are looking at. And just for a sort of a summary, how am I doing on time? Oh, perfect. So for a summary here, you know, we started this to look at SI traceable measurements. It turns out it's exploded into a whole range of other areas. We talked about one of the big benefits here initially was that we have this tremendously broadband source, our receiver here, right? I can basically, with very easily measure from about, a few megahertz up to a terahertz with one vapor cell, so very broadband. It allows us to do an SI traceable measurement. It also allows us to make a measurement independent of any other technique out there, which is nice from a traceability viewpoint. We're looking at making these things small. We're already getting them down to millimeter size. The next step is making the lasers and everything else small. And it has a huge dynamic range, as far as I didn't talk too much about, but we've measured about, 2 microvolts per meter in the lab, and we've also measured up to 10 kilovolts per meter in the lab. So a huge dynamic range and a huge frequency range. One thing that I alluded to a little bit, our instantaneous bandwidth isn't great. It's not like your cell phone. Here, very easily, we can get about a 6 megahertz signal through the atoms. If we work a little bit, we can get it up to about 10 or maybe 12 megahertz. And the question is, how much higher in bandwidth can we do from that? Or more importantly, are there some applications where that lower bandwidth may be okay? And I think the lower frequency is one aspect of that. I like to always leave a lecture now with a quote from a Nobel laureate. And one of my favorite laureates is Dylan, who said, there's no success like failure, but failure is no success at all. This I think, sums up my project. I lobbied NIST for probably 5 years to try to get a dime, and all of other government agencies who wouldn't give us the time of day until we could actually show a proof of concept. The idea here, if you got a good idea, and if you give it time and enough effort, you can be successful. Question is, what do you mean by success? Some people think money. I think doing some cool science is successful. So for that, I think this project's been really successful. But with that, it's not just, one person having good ideas and working hard at it. You got to have a really good team. And this is the group of us at NIST now. I have a great team, highly motivated, highly intelligent people. And we're doing all kind of cool things at the lab. So I want to thank them and thank you guys. And I'd be happy to try to answer any questions you have on our sensors. So.
Thank you very much,
Yep.
Chris. That was a wonderful lecture. A fantastic project. Absolutely. I think there are many amazing people here. So we'll open up the lecture for questions.
Yes.
Compared to a dipole antenna, how does the effective area of this antenna work?
Well, I get that question asked a lot, and I'll answer it as vaguely as I've answered it in the past, is that I can't really think about effective area here, right? Because I'm not talking about, this thing really doesn't have a gain. If I think gain versus effective area, 2 pi, r in there somewhere, this is not behaving like your classical antenna, so you have to be careful about how you interact with it. With that said, I would argue that if you have a well-matched resonant dipole, this ain't gonna beat it, right? That's a very good, however, if you need something broadband, having a resonant dipole is difficult, or if you're trying to do measurements at megahertz or below, you need a lot of space for that resonant dipole. So there are certain areas it's not going to beat a resonant dipole antenna, but what it will beat is any other electrical small antenna that's out there. So, yeah.
What limits the bandwidth to 10 megahertz? Is it the natural line width?
Yeah, it's basically the atomic response. I've got to drive these things up to a Rydberg state, and then really the true limiting factor is how fast can I drive those atoms out of that Rydberg state so I have a new set of atoms to interact with. And so there's ways that, you can heat these cells up a little bit and you increase the bandwidth because you're driving the atoms in and out. They're moving faster at some faster velocity. So it's really the atomic property of that atom that's sort of governing our bandwidth right now. Yeah.
What type of sensitivity was achieved at 20 kilohertz?
20 kilohertz, I think right now, it was a very crude measurement that we did. Let's see, I think we're at 10 millivolts per meter, I think is what it was. Yep, 10 millivolts per meter. Yep, please.
So you talked about the challenges of getting that second laser to a smaller size. Which makes me ask the question, is there anything special about the laser frequencies in this application?
Well, that's a good point. I didn't get into the subtleties here. Everything I talked about, remember my energy state diagram? I had 2 optical beams get me to the Rydberg state. For that scheme, you need a blue or a green laser, a visible laser, or either rubidium or cesium. Those blue or green visible lasers are hard to come by in a diode that has enough power to give us. With that said, us and other groups are looking at now, we call it multiple photon schemes, where we use 3 different color lights to drive up to the Rydberg state. And if you look at the color lights you need to do that, those are already, I wouldn't call them chip scale yet, but they're already diode lasers. One requires like a 1260 laser, a 780, and a 790, which are already almost chip scale. So by choosing different atomic excitation schemes to Rydberg state, you can overcome this. And so people are looking at, if you're really trying to make something compact, maybe you go to a different scheme so you don't need visible lasers. Yeah, Ed?
Is there any analogous technology or fundamental piece of science that would allow measurement of a magnetic field in an analogous way?
Yeah, and we've thought about that and want to do this measurement. There's a group at NIST that does magnetic field measurements, and they can make extremely sensitive magnetic field measurements. And I thought, well, great. If we take our magnetic field source, our electric field source, I could determine C. The problem is, because of C, that magnetic field and the electric field are such drastically different orders of magnitude, it becomes difficult. And these magnetic sensors that are very sensitive actually only work to about 1 megahertz. So for me to generate a strong enough electric field in some environment below 1 megahertz that I could then use to measure magnetic field, there's some physics that sort of doesn't allow these to overlap in the right frequency range. Yep. C. You can't get over C.
The second
Yeah.
follow-up, you claimed that we're done with artifacts. That means you've forgotten about your beer gauge.
Yes, that's right, yes. I'm not done with that, but yes, thank you. Other questions? Yeah, please.
Is there any noise added by the Rydberg cell?
There's a different type of noise, right? There's all this laser noise and things like that, and then there's some atomic physics noise that you have to worry about. So in principle, if we had an ideal atomic system, we should do better than what you could do with a conventional receiver. But it all depends on the frequency range and things like that. But there are other noise sources different than what we conventionally think of that we have to worry about. Yep.
How long does it take to be reconfigured to measure different frequencies?
That's a very good question, and I will say it depends. And then when I say it depends, what I talked about, this Altertown splitting, that requires that atom to be tuned to a particular atomic state so that the next transition is an on-resonant RF transition. So I have to be able to tune that blue or green laser quick enough to get to those different atomic states. Okay, and people are looking at ways, I should argue that I didn't show results here. We're using frequency cones now. Well, we can take I think it's our green light, and we can spread it over a range of frequencies and do simultaneous measurements at once now. So we can simultaneously measure several frequencies at once. And they don't interfere because, this atom is a beautiful resonant structure with all these really nice, well-defined resonances, and you can take advantage of that. If you're doing it that approach, and with this Altertown's approach, it allows you to make these very, very sensitive field measurements. If you are just trying to measure a field and you're not too much concerned with sensitivity, you can just park the laser at one wavelength, and we do something called Stark shifting. That if we have this a Rydberg state and we hit it with an RF field that's off resonance, if that field is high enough, in fact, that's what this measurement here has done. Right here, this is basically the Stark effect, that we're measuring a DC field is nowhere near resonance with the atom, but I generate this EIT, and as I turn on a field, if the field's strong enough, it starts shifting that atomic state, and I can measure that shift, and I can show that shift is directly related to the polarizability of the atom. So once again, it's a traceable measurement, but in order to do this, so it's instantaneous, in that case, it's instantaneously, but I have to have a high enough field for me to take on this approach here. So, yep. Yep.
In other applications, you had mentioned the plasma sensor. Are you embedding the vapor cell in a plasma, and then are you measuring anything besides electron field?
Yeah, I didn't show that here, but we have essentially done that. That it was a cool little experiment. I took a vapor cell and I put cesium and rubidium atoms in it. And basically, I took lasers and ionized and generated a plasma of all the rubidium, or all the cesium atoms that were in this vapor cell. Then I turned on the lasers for the rubidium atoms, and I used the rubidium atoms to measure the plasma of the cesium. And you can actually get the really nice field distributions in these plasmas and so forth. But yeah, there's a couple people out there, we just have moved on away from the plasma, but you could, in principle, put these in plasmas and measure plasmas. Especially if you, and the beauty of it, I think here is that, as you can see, that plasma usually have high fields. So this dark effect here is the way that we actually measure plasmas. That you have high field already, you can take advantage of it here. So. Yep, please.
I have a question about the imaging results. So that's achieved by measuring the electric field intensity and distributed by the logo, the NIST logo you have developed.
Yeah. So how that works is, I'll show it and I'll try to explain it because it's a little too complicated. But what's going on here is this is all based on a fluorescence experiment. Whoops, I missed it. Let Microsoft catch up. Here it is. So it's fairly simple. What we're generating, in this case here, we took a beam and flattened it out, made like a flat beam, ran it through the vapor cell, and if you think about it, we generated a bazillion EIT lines inside this vapor cell. When we excite these atoms up to this Rydberg state, and they interact with this electric field, they actually fluoresce. And the amount at which they fluoresce is a function of the electric field strength. So with the camera, we can basically monitor the electric field anywhere inside this vapor cell. And I'm not going to talk about it here because we have a paper we're trying to submit, hopefully by today, maybe next week, where we actually now can do localized imaging. We can actually image the field at any point inside, the structure, inside the vapor cell to about 50 microns. So we can do really local imaging such that we could look at surface charge effects and look at surface charges on metal and things like, or on glass surfaces and so forth. So it's a similar approach, but it's based on fluorescence that we're actually detecting with the camera. So the camera's calculating the fluorescence coming off these basically EIT lines here. Yeah. Other questions or comments? Let me just say that if anyone's interested, just email me. We had a paper came out just probably 2 months ago in Nature that sort of summarizes the last 10, 15 years of this field. I'd be happy to send it to you. And so, of course, we have a slew of other papers. Don't hesitate, call me, email me. I'd be happy to answer any questions. Like I said, that's our mission. If you want to start a lab, you can come out and show you what we're doing. Go home and make your own lab. Yeah. Thanks. Unless there's any other questions, thank you very much.
I'm sure I speak for everyone when I can say it's been a pleasure to have you as our 12th Conduct Fellow.
No, I'm
Thank you very
honored
much.
by it. I
Please
sure
see the
appreciate it.
demo, and there'll be opportunities for questions, and this will close our lecture. Thank you.
Yep, thank you. Good.